Okay, so I assume you can hear from me, right? So it's okay, right? So in case you have any technical issues, so just let me know, okay? So for today's lecture, so we are going to finish like the dynamics and transport of the single particle, right? And then we'll move on to talk about the thermodynamics, okay, of the aerosols. But before we talk about the thermodynamics, let's finish like the transport. So before the holiday, so somehow we stopped at this we call the Stokes number, right? So you still remember the Stokes number. So we are looking at the ratio, right, of a stopping distance S over L. L is some characteristic length scales. So somehow you can rewrite the equation like this is the tau times V naught. Tau, if you remember, this is the relaxation time of your particle, and then V naught is kind of the velocity, right, of your fluid or of your particle, and then it's divided by this L. And if you remember, so this is the Stokes number, okay? So you have this expression. So if you just remember the characteristic time scale, or we call the relaxation time scale. So this is related to this expression. So this is just to replace the relaxation times. So by using the density of your particle, the diameter of your particle to the square. So remember, we need to do the Cunningham correction factors. And then this is the viscosity, right, of your fluid here. So, but the idea is this Stokes number, right? So we can use this like a parameter, right, to determine or to design we call the cutoff, right, particle size in the impactor. Basically means we try to collect the particle, right, by impaction. But one thing is that if you still remember is if our Stokes number is right, is much larger than 1. So that means the particle, right? So you cannot follow the flow, and then so you can remove the particle, right, or collect the particle by impaction. So if you remember, so when the Stokes number is large, right, so that means your stopping distance is large, right, compared to your characteristic length scale, right, L here. But let's say if your Stokes number is small, that means on the other extreme, right, on the other side, so basically means we can argue, right, the particle can kind of adopt the changes, right, in the fluid velocity very quickly. So therefore, you will not collect the particle by impaction. So this is how people use this we call the Stokes number, right, to design the cutoff particle size for in the impactor. So before we finish, so we want to talk about some impaction, okay, using this Stokes number. So most of the time, so we can collect the particle by impaction, right? So like we mentioned, right? So for example, so this is a simple device. Okay, so then you have a flow coming in with your particle. So this is kind of the streamline, right? So we can argue this is your streamline. So sorry for that. So let me try to draw the streamline for you. So this is the streamline, okay? So of course, we know for small particle, right? That means the Stokes number is small. So basically, they can just follow the streamline without collection. But for large particle, right? So because of the inertia, right, or the momentum, so they cannot adjust their flow, right, or the velocity. So they can collect it by, we call the impaction, right? So therefore, impaction is very important. It's kind of an important mechanism for particle collection, especially for large particle. For large particle collection. So most of the time, if we want to collect some large particle, so we will use this impaction, okay? So this is the effective for the large particle collection. So therefore, the Stokes number now come in, okay? So when you want to design an impactor, right, to collect the particle, okay? So to do this, so you can calculate this Stokes number, right, for your particle size. So now we want to change is the L. So if you remember the L, we define is more like a characteristic length scales. But for the impactor, okay, for the impactor cases, so we can define this L, this characteristic length. We can define this as the nozzle diameter. We can use this we call the nozzle. So you can substitute this nozzle diameter. What's the meaning of the nozzle diameter? Means that this is like the nozzle, right? So this is the nozzle. So you can use this the nozzle diameter for your L. Okay. So then you can calculate the Stokes number, okay, for your impactor. So in this case. So therefore, you can see this Stokes number, right? So when the Stokes number is increased, right? So then you can collect the particle by impaction. So therefore, we can define a parameter called the impaction efficiency. Impaction efficiency. So of course, you know this impaction efficiency, right? So will be depends on the Stokes number, right, for your impactor. So therefore, this impaction efficiency, so will be a function of your Stokes number, right? And also you can imagine, right? So when your Stokes number increase, so your efficiency will also increase, right? Right, so because when the Stokes number increase, right, so become larger and larger, right? So you can collect the particle, right, and more efficient, right? So therefore, these for this we call the inertia impaction. So for impactor, right? So we want to tell you, so what's your particle size, right? We call the cutoff diameter. So that means that if the particle, so let's say we can call a cutoff size of your impactor. So what's the meaning of this? We call the cutoff size of the diameter. Okay. So basically, mean this cutoff size means if this particle size, okay, if the particle size is smaller than this, we call the cutoff size, smaller than this, so that means they will not be collected. If your particle size is larger than this cutoff size of your impactor, so they will be collected. Okay, so that means we can consider an ideal situation. So let's say an ideal situation. So your reactor or your impactor, right, can have a sharp cutoff size. We call the sharp cutoff. So what that means is that all the particle or aerosol, say larger than certain size, that means a larger or greater than this, we call the cutoff size. Certain size means that you can later we call this a cutoff size. So if the particle size are larger than this certain size, so will be collected. All particles greater than a certain size are collected. So that means on the other hand, right? So if all the particles smaller than this certain size, so they just a plus rule, so no collection. Okay. So therefore we call this sharp cutoff, or we call this a cutoff size, okay, or this a certain size. So we call them, we give a name called cutoff size. And then we call D50. Okay. So what's that mean? So let me draw a figure for you. So the y-axis here, so we call this a collection efficiency. Okay, so for your y-axis is your collection efficiency. So you can have 0, 50, and 100 collection efficiency. Okay, so kind of the fraction of your particle being collected, right, by impaction. And then your x-axis here is we call the Stokes number. It's the Stokes number of your impactor. Okay. So sometimes people take the square root. So take the square root of your Stokes number, but basically the Stokes number. So what's the meaning of this? We call the ideal situation. Is you can see, right? So you can define a Stokes number, right? We call the sharp cutoff. Or I can draw this as say red line you may see here. So because you know the Stokes number actually is also a function of your particle size, right? So but the idea is so you can see for this we call the ideal sharp cutoff, okay, for a given size. So you can see that so when the size smaller than this we call the sharp cutoff diameter, right? So there will be no correction happen, right? So therefore your correction efficiency is called 0. But when your particle size, so remember this is also a function of your particle size, right? So when your particle size larger than this Stokes number, right, or larger than this we call the certain size or cutoff size, so you can see that we have 100% correction efficiency. Okay, so this is we call the ideal case, right? This is the ideal case. But of course, we know in reality, right? So this will not happen, right? So you will not have this sharp cutoff here, right? So therefore, you can more likely you will see here. You will see something like this. So let me try to draw. So in reality, so more or less, you will see a curve like this. Okay. So let me give you this we call the dotted line. So in reality, you will more see this we call the red dashed line or dotted line here. So that means you can always see that for some particle, right, smaller than this cutoff size, so you'll also be collected. Because there will be some probability, right? Some smaller particle, right? So can be collected, right? So below this we call the cutoff size. And also you can argue, right, some larger particle, right? So some particle size larger than this cutoff size can escape, right? Or can go through, right? So let's say this is called the oversize. That means the size of the particle, right, larger than this cutoff size. We call this the oversized particle can get through, right, in reality. So no correction, right? So no correction. And of course, some smaller particle, right, can also be collected, right? So this is we call the underside. So this is a more like the real situation. Okay, so you will see. So therefore, you will not find a very sharp, we call the cutoff size, but you always see a curve like this. So therefore, usually people define, okay, they call the DP50. Okay, DP50. So you're looking at say 50% collection efficiency. Okay, so therefore, in the real world, so when you say the cutoff size of your particle, right, of your diameter of your impactor, okay, so you will use this, we call the 50% collection efficiency, okay. So when you use the Stokes number, that gives you 50% collection efficiency. Okay, because you never get this, we call the ideal situation. Okay. So this is called the impactor. So therefore, this Stokes number is a very useful parameter, okay, or important parameter for particle collection, okay. So especially by you want to collect some large particles, okay, by impaction. And then, so one of the devices that we are going always to use to collect the particle by impaction is, of course, we call the impactor, right? So this is called the impactor. So I think in the lecture notes, we show some of the instrument, right? So basically, it's a simple device with a nozzle. You know, this is an impaction plate, okay, the nozzle, and then this is kind of the streamline. Small particle can pass through, larger particle can be collected by the inertia impaction. Okay. So this is just give you some application, okay, of this we call the impaction or the Stokes number, okay. So any question? So just to give you some application. So when people talk about impaction or impactor, when you design an impactor, you want to know the what size of the particle being collected, right, by your impactor. So you look for this cutoff size, and then this is kind of a link to your Stokes number. So now you have some ideas here. Is that okay? So any question from the class? So this is just to give you the application for this, we call the Stokes number. Okay. So now this is impaction, right? Or inertia impaction. So it's a good or excellent, right, mechanism or method for collecting large particle. So how about if you want to collect some small particle? So because of small particle, right? So we know, so they can always follow the streamline, like the streamline. So it's very difficult, right, to collect the small particle by impaction. So that would be another approach to collect a smaller particle. So before we talk about, so first we want to look at, it's called the diffusion, okay? So particle diffusion. So particle diffusion. Of course, you can imagine, right? So we have a particle. This is your particle, and then we have the gas molecule around. And then you can imagine, right? The particle will be continuously bombarded by this small gas molecule, right? So basically, you can imagine, right? Your gas molecule will hit, right, the surface of the particle or bombard the particle, right? So in that case, you can argue, right? They can cause some force, right? Or eventually they will create some we call the random motion, right? Because when you have this collision happen, right? So then you exert some force on this particle. So then eventually you can, we know that this can create some we call the random motion, or we kind of call the irregular walk, right? So this is the name. We call this we call the Brownian motion. So I think you know this, right? So called the Brownian motion, right? Okay. So the Brownian motion, so like I mentioned, so this will be more important, right, for small particle. So in just to give you a quick idea, so when we talk about the Brownian motion, okay, so this is important for particle size, say smaller than 100 nanometer. So it's more like important say for some of your particle smaller than 100 nanometer. Okay. So when you say this is called the Brownian motion or diffusion, okay. And then sometimes when we say this is called a Brownian motion, but when we say diffusion, okay, so what's the meaning of diffusion? So basically, diffusion means that the net movement, right? The net movement caused by the Brownian motion, okay? We call the net movement, right? Caused by this Brownian motion. Okay. So this is the meaning of Brownian motion and diffusion. And of course, we don't go into the details of how to derive this the Brownian motion. So you can find the details in the textbook. We show you the diffusion coefficient. Okay. So because the idea is your Brownian motion, right, can be somehow categorized by we call the diffusion coefficient. Okay. So you can have this, we call this a diffusion coefficient. Called D. So will be equal to so you may have seen this equation before. So this is called the diffusion coefficient, okay, of a particle. So K is we call the Boltzmann constant, right? The small k here. So maybe let me write down just here. So hope that you can see this is just the Boltzmann's constant. So this small k is called the Boltzmann's constant. And then T is the temperature, right? And then Cc now you know this is called the Cunningham correction factor. Okay, and then this is zeta, right? So this is called the viscosity of your fluid. And then the dP is the diameter, right, of your particle. So more important, let me highlight it. This is your, say, your particle diameter. So of course, I think this equation, right, intuitively makes sense to you, right? So remember, this diffusion coefficient, right, kind of describe you the net movement, right, caused by the Brownian motion, right, or the diffusion. So of course, you have a higher temperature, okay, so you have a more diffusion, you have more energy, you have a larger diffusion coefficient, and then of course, you have a smaller particle, right, so you have a larger diffusion coefficient, right? So therefore, you can see this is kind of and intuitively makes sense to you, right? So then we want to give you some just a qualitative analysis. So let's say we want to have some discussion about, for example, if we look at the displacement of some particle from the Brownian motion. So we want to look at this displacement, okay, due to this Brownian motion. So you can imagine I can draw a line here. Say this is the center, and then say this is positive x, and then this is the negative x. I just consider in the x direction, okay. And then if you remember, initially I put some particle at the center, so you can have different size of your particle here. And then you can also look at the displacement, right? So kind of we can calculate, one way to calculate the displacement, we can calculate, we call the root mean square, right? You can look at the root mean square displacement is equal to the square root. We're taking the square root 2 times d. D is the diffusion coefficient, and then times the time t, right? Depends on that time. Okay. So of course, you know that when the time proceeds, right? So some particle will just move around, and some will be here, right? So you just argue, right? So the particle just randomly, right? And then we kind of calculate this. We call the root mean square distance, right? But of course, you can see if at a given time, right? So if you have different particle with different size, so of course the displacement, right, will be very different. So for smaller particle, right? So for smaller particle, so you can argue, right? So they will have a larger diffusion coefficient d, right? So therefore, they will have longer displacement. Okay. So just qualitatively. So if this is your particle size, so let's say I just say this is small. So let's say this is a 5 nanometer, and then I have some large particle, 300 nanometers. So of course, you can use that equation, right, diffusion coefficient, right, to calculate this equation, right, to calculate the diffusion coefficient. But the idea is if you have a smaller size, so you have a larger or large diffusion coefficient. For large particle, so you have a small diffusion coefficient. And then eventually, if you look at the displacement, right? So therefore, you look at this equation, so that will be long, and then there will be short, right? So this is just a qualitative. But one thing is, we want to maybe more quantitative is, remember, so when we talk about to remove the particle, right? So for a large particle, okay, we want to remove by, say, by impaction or by gravity, okay? And then for small particles, so maybe we can want to remove by this, we call the Brownian motion, okay? So then maybe we can compare these two processes, okay? So one thing is we want to compare like this Brownian motion, and also the one we talk about like by the settling velocity, right? That means due to this gravity settling. So we want to compare this Brownian motion. So versus like the settling velocity, or we call the gravity settling. So we want to compare these two processes, okay? One thing we can also compare is like the displacement, right, due to these two processes, okay? For the diffusion, so you can calculate this root mean square displacement, right? So you can calculate using the equation I just showed here. And then for the gravity settling, right? So you know we can calculate, right, for a particle size. So you can calculate the settling velocity, right? So then the displacement, so you can say is your terminal velocity times t, right? So you can compare these two displacement, okay, for a given time t, right? So let's say I do the calculation here is let's say we calculate in 1 minute, okay, and then for different particle size. So then I can construct a table. So let's say this is your particle size, the diameter in micron. So it's a different particle size from 0.001, 0.01, 0.1, 1, 10, and then 100. So this is your different particle size. Okay. So for different particle size, so of course I can calculate, right, the diffusion coefficient. Okay, the diffusion coefficient. So I just show you the result. So you don't need to worry too much about like the exact number, but if you look at the order of magnitude, of course, we know, right? So for smaller particle, so you will have a larger diffusion coefficient, right? So this is, you say, if you go down to say 0.001 micron, so your diffusion coefficient is 10 to minus 6. But if you go up, right, so when your size increase, right, the diffusion coefficient, right, of course, it will decrease. And then you can say for a 10 PM10, so it now become 10 to the power 12, okay? So if I look at the displacement here, that means the Brownian motion, right? The displacement due to the Brownian motion, say in 1 minute. So let's say this is a meter per second. So the unit here. So your root mean square, the displacement from the Brownian motion, say are expressed in 1 minute, and then this is a meter. So you will find that, so this will be 2 to. So I think this result may not be surprising, right, to you. Of course, for smaller particles, so you will have a larger displacement, right, from the Brownian motion. You can see this is 0.02 meter, okay, for a 0.001 micron. And then, of course, when your size increase, so your diffusion coefficient decrease, and also your displacement will also decrease. But when you say it's a PM10 now, it's only have a point, say it's the 10 to the power minus 5 meters. So you can see how the change in the order of magnitude. Okay. So now this is called the Brownian motion, right? So we now can look at the gravity, right? Settling. Okay. So we just so we show you, so you can calculate your settling velocity for different size. Okay, I just times the distance. This is y. Okay, the distance they travel or settling. Okay. So if you calculate this, so again, don't worry about too much the exact number. So why? Remember, this is the kind of the distance fallen, right, by the particle due to the gravity, right, at its terminal velocity. So you can see for a very small particle, of course, the gravity, right, the influence by the gravity is insignificant. So you only travel by 10 to the power minus 7 by meter here. But you can see that for a large particle, say PM10, so for 1 minute in this case, so you can travel 0.3 meters, right, due to this gravity here. So what's the basic concept or important message? You can take the ratio, right, between these two. Say we take the Brownian motion, right, to the gravity settling in this case. So you can take the ratio to see the relative importance, right, of these two processes. So you can find that so don't worry, I just take the order of magnitude here. But you can, if you just take the ratio, okay, across the particle size. So it's not surprising to see, right? For small particle, so the Brownian motion, right, will be the dominant. Okay. For large particle, so the gravity will be dominant. So therefore, you can see if you're just looking at the ratio, right? So this is larger than 1. So basically means the Brownian motion, right, is the dominant process. Or you can argue, right? So the diffusion is dominant, right? And then for large particle, right? So the ratio become less than 1, right? So that means that in this case, for gravity dominant. So that means that you can argue, right? Say for PM1, if you're looking at some of PM1 particle, right? So you will start thinking about the gravity. So for particles smaller than PM1, so you're thinking about the diffusion, right? So therefore, one last thing is, so in general, you will see a graph like this. So let's say this is the particle size or particle diameter in this case. It means our dp. So let's say this is 10, 100, 1,000, 10,000, and 100,000. So we are in this nanometer, okay? So let's say this is nanometer. I can also give you, say this is 1, 10, 100 in micron. Okay, so in case that you're interested in the micron, so we are looking at the size like this. And then if you look at the distance travel, so just say just the distance travel. So you just want to highlight one thing is for small particle, so you will find that you more or less you see a curve like this, okay? So this is called the diffusion. So the idea is as for small particle, okay? So it can travel a large distance, okay, by the diffusion, or we call the diffusion dominant. And then for a large particle, so basically, you will just very sensitive to the size or the mass of the volume. So you will just something like this. So because at the same scale, okay, at the same scale, you can see PM1, you already travel the same distance, okay, by a small particle. And for a very large particle, right? So you can imagine, right, the distance traveled by a larger particle, right? So even larger. So therefore, the idea for this graph is so this is remain the same. So just another way to present this is for PM1, okay, or larger than PM1. So we always think about the gravity, okay, dominant. And then for smaller particle, okay, say less than PM1, okay, so then we will talk about the diffusion. So now you can see that for small particle, right? So you can kind of remove, you can think about, we can remove the small particle, right, by diffusion process, okay? So how we can collect this small particle? So one way we can collect this small particle is we call the collection, say we call the diffusion screen, okay? Diffusion screen, okay? So what that means, you can argue. So let's say I have an aerosol, say coming in. So this is the aerosol distribution. This we target small particles, right? So this is a 10 to 100 nanometer. So this is aerosol coming in. So you can pass through more like a screen or a net. So you can have a net, the screen, but you have a more like a, you see, you have kind of this net, okay, or we call this screen, okay. So this diffusion screen, okay, can help you to remove the small particle by diffusion. Okay, so basically your small particle passing through this diffusion screen, right? Because of the space is narrow, so they can quickly remove by the diffusion, right, to the screen. So therefore, in this case, so let's say in original size, you still have this. This is your original aerosol in. But after that, so you can remove the particle, right, by diffusion. Of course, a smaller particle, right, can be removed by these, right, diffusion screen more efficient, right, or more effectively, right. So what you will have is you kind of like this, okay. So basically, this is your aerosol out. So basically means that you imagine, right, smaller particle, right? So they have a larger diffusion coefficient. They can be more easily, right, removed by this screen by diffusion. Then you pass through this screen. So therefore, smaller particle, right, will be removed more efficient, right? And then of course, some larger particle will just still pass through the screen. So you see this, the smaller particle, right? They can be removed by diffusion. So therefore, one way to collect this, we call the small particle. You can do this, we call using this, we call the diffusion screen here. Okay. But I think that the main message for this, if you don't worry too much about the number here, is if you really want to have some number in your mind, is when your particle say larger than 1 micron, then you start thinking about the gravity settling. Okay. When your particles say less than, say, 1 micron, 1 micron, or say more precisely, say less than 100 nanometer, right? Less than 100 nanometer, then you start thinking about the Brownian motion. So this is more like the message here. Okay. So any questions so far? So I think this is not too intuitive. You get this idea, right? So small particle is important by diffusion, but I think more important is that to give you some number, okay, to give you some kind of a quick references, okay. So when we talk about the diffusion or the gravity settling, so you have some quick ideas. Okay. Okay. So now we're going to stop here for the dynamics or the transport of a single particle. Then now we move on to talk about some of thermodynamics. Okay. So I'm sure you have taken the thermodynamics courses, right, before. Here, we more focus on to just give you a quick overview or refresh your memory. And then we try to talk about the thermodynamics, okay, from an aerosol perspective, okay. But just want to, at the same time, just give you a quick overview of the thermodynamics, okay. But remember, we more focus on, okay. So I got a question. Okay, so when we say remove small particle by diffusion, okay, does the large particle pass through the diffusion screen? Okay. So for this diffusion screen, so you are right. So your argument, right, is your particle will be collected by this one, but not showing here is you can imagine is the diffusion screen is something like this. You have a multiple channel. when your aerosol go through, right, like this. Of course, you can argue your large particle, right, can be collected also, right? If this is your main flow, so your particle can be somehow also deviated from the flow by the gravity, right? But you can imagine, right, this displacement, right, would be more significant for small particle, right, by diffusion. And then large particle, in this case, you don't change the direction of your flow. So you can see my argument, right? So for this screen, so basically you have a more like your flows just come across with this channel, right? So you don't make the change of your flow direction. So then if you look at the displacement here, right? This is mainly due to the diffusion, right? If it can answer your question. So basically the large particle kind of follow the streamline here in this case, because we don't bang the flow. Do I answer your question? So of course some particle may collect it, you're right, but not that efficient compared to smaller particle. To answer your question about, yes, some large particle will also be trapped. Okay, of course that will be, but not that significant. Okay, good. So because the idea is to collect a large particle is you remember the interaction. We need to kind of change the flow, right? You need to kind of change the direction of your flow. If you don't change the direction of your flow, you just flow in this position, right? So basically, large and small particle just go through the channel. So I hope that I answered your question. Any other question? Okay, good. So now let's look at the thermodynamics. Okay, so thermodynamics. So we can start with some air parcel. Okay, so of course when we talk about aerosol, so we talk about some air parcel. So of course you can say you have an air parcel here. So we always talk about this. So you can have some internal energy, right? So internal energy. So I think I will quickly go through this part. I'm sure you have some ideas. So, but if you have any questions, so feel free to stop me anytime. So you have some internal energy U. Okay. So when you talk about the internal energy, right? So we are talking about some kinetic energy and also the potential energy, right, of the atoms or molecules, right, in a system. Okay. So when you talk about this internal energy, we are talking about some kinetic energy plus some potential energy of the atoms, or we call the molecules, or the species, right, in the system, in your system. And also every time, so when we talk about air parcel, right, so we consider a scenario, right, is your air parcel, right? So we assume there's a closed system, right? So we assume a closed system. So I think we know the closed system means that basically you don't have any mass exchange, right, between your air parcel and your surrounding, right? No mass exchange between the air parcel and it's a surrounding, right? Okay. And also, so when we saw about the internal energy, so of course, we also talk about the change of the internal energy, right? U. So there will be two processes, right? I think we learned this from the first law of thermodynamics. Okay, so the du change in your internal energy, right? So there will be two processes, right? One is called the dq plus the dw, right? dq is a kind of the flux, right, or the amount of the heat, right? You can say in this case, so say for example, you can say this is the amount of the heat being absorbed by the system, right? And also the W, right, is the amount of work that is done onto the system, right? So or onto the surroundings, it depends. Okay, so this is, I think you got this before, right? Q means the heat flux, the heat, right? And then the W is called the work done. And also, so of course, we can have some discussion here. So when we say there's a work done, so I think you see this equation before, right? So work done equal to minus P times the dV, right? So let's say this is a work done, say at constant temperature and pressure. So let's say we focus on our discussion, say at constant, say temperature and pressure. Okay, so the dW, the work done, right? So will be equal to minus P times the dV. Okay. So for example, you can argue, right? So if your air parcel expands, your air parcel expands, so what will happen? So that means that in this case, when your air parcel expands, your dV, right? V is the volume, right? P is the pressure, V is the volume. So then if we quickly say if your parcels expand, right? So when you expand, your volume increase, right? So therefore your dV would be positive, right? dV means the change in your volume, right? It's positive, okay? So that means the work done, of course, you times the value here, right? This is a positive, positive. This is minus sign. So of course, your work done would be negative, right? Onto your system. Okay. So you can also talk about the dq. So the dq is a kind of the flux, right? The heat. Okay. So at constant temperature and pressure, there will be T times the S. T is the temperature. S is we know the S is the entropy, right? Entropy of your system. So of course, you can have a different interpretation about the entropy of the system. But one thing to think about the entropy, right? So it's a kind of the degree of disorder, right? Of all the elements in your system, right? So this entropy is kind of the measure, right, of the degree of we call the disorder of the element in the system. Okay. So basically means more disorder, right? So you have a greater entropy. Okay. So this is the case. So if you just put these two terms back to the equation. Okay, so you can put these two terms back to this equation. Okay, so then you can get this, we call the du equal to Tds minus Pdv. Of course, in this case, so we assume a situation is that we are at constant temperature and pressure here. Okay. So this is, I think this is, you have seen this equation before for a closed system, and then we consider an air parcel, okay, for a closed system. But now the thing is, so So this is may not always be the case, right? Of course, you can have the mass exchange, okay, with your surrounding. So therefore, we are not always talking about closed system, okay. So that in that case, in this case, then we will looking at a system called the open system. Open system, okay. So that means in this case, the open system is kind of your composition is changing, okay, or you can have a variable composition. So you have a variable composition. So that means you can argue, right? So the composition of your species or the concentration of your species can change in your system. So when you talk about the composition change, so you can also argue, right? The number of mole in this case, the number of mole of your species can change, right? You can think about another way. So the number of mole, give me the concentration of your species. So they can change. So therefore, now when you look at your internal energy, right? So now your internal energy, so of course, now will be a function. Of course, that will be related to your entropy, your volume, okay? And also now, because you allow the species, right, the composition change. So therefore, you'll be, depends on your species, right? You can have N1, N2, blah, 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 to Nk, right? So because your concentration of your species will change here. So therefore, now you need to add this term. And also your internal energy, right, will be also a function of the number of your species, right? The number of mole of your species. And then if you take the differential of this internal energy, so if I take this one, so I think you have some idea about the partial derivative. So let me write down the equation and talk to you about this. So of course, we can take the derivative, right? Total derivative, okay, or differential of this u. So then you can see the change of your internal energy, right? Will be, for example, this will be your partial u, partial s, right? So look at your change in your entropy, right? But holding other parameter constant, right? So if you remember, so you just look at how the change of your entropy, right, affects your internal energy, right? But whole other function, right, or other factor constant, in this case, the volume, right? And also the composition is the same, right? So you hold this constant, and then just look at how your internal energy change with your entropy, right? In this case. And this one is just you're looking at how the internal energy change with your volume, right? The volume change, right? And then you hold your entropy, right? And also the composition the same, okay? So now this one you look at, because I have number of species, right? So you look at how your internal energy change, right? With respect to certain specific species, right? And then holding the entropy and also the volume and also other species, right? The same. And then because you have k number of species, right? You just a summation, right? To k here, okay? You just a whole other species are constant. Right? So this is called the total differential of your u here. And then if you compare to somehow the terms here, so you can also find that this term, okay, so that will be equal to your temperature. And then this term will be equal to your pressure, okay? Pressure terms here. And then if you can go back this equation to a closed system, right? So when you have a closed system, so what's that mean? So that means sorry, I'm missing the end, right? So for a closed system, basically means your changes of your species, right? This is a dni will be equal to 0. So that this term for a closed system will become disappear, right? So then you just get this term. And then you can compare to this term to here, right? At constant temperature and pressure. So that would be, this is T, and then this is the pressure here. And now we just want to define a term. Here is we give a definition. We call this term called the chemical potential, okay, of your species. So when you say your chemical potential, what's that mean? So let's say we define the chemical potential of a species I, and then we put a name called the mu1, mu I. So we just define this term, okay, as the chemical potential of your species I. So basically means you are looking at the chemical potential. Basically means that you are looking at how the species, right, contribute to your internal energy. Okay. And then of course, by the definition, you're looking at so how your internal energy change, right, with respect to your species, right, and then holding, say, the entropy, the volume, and also all other species, right, it's the constant that does change. And then we define this, we call the chemical potential. This helps us to understand so how the species, right, contribute to your internal energy. So then if you have this by this definition, and then you can compare this one. So this is just the temperature. So this is the pressure term. If you agree with this, so you can come up with the equation. So basically, you have the same equation, but now because we are considered an open system, basically you just add the chemical potential, right, of your species, right, this term here. So this is more like the equation, okay, for an open system here. Or you can say this as allowed as a variable composition in your system. So then you just add these terms here. Okay. So this is a closed system. So this is just a system. Say it's open means that you have a variable composition here. Okay. So now, so one thing is we're going to talk about is this equation here. So later we're going to introduce a term I think you heard about called the Gibbs free energy, right? Or free energy or free entropy. The idea is you can see here is so you know it's difficult for us to measure, right, the internal energy, or you can argue, right, the entropy and the volume. So these two parameters, like the entropy and the volume, right? So you can imagine it's not very easy to measure, right? If you want to look at how the change for the internal energy, right? So you need to measure, right, the change in your entropy, but also the change in your volume, right? So if you consider like in the aerosol or air parcel, right? Okay, so these are parameters that you are not very easy to measure, right? It's difficult to measure these two parameters. The entropy, right? Entropy of your air parcel or aerosol or entropy or the change in the volume of your air parcel or your system. So therefore, in this case, for atmospheric science, okay, so we want to measure its temperature and pressure. So that will be more easier to do this. So therefore, so we're going to make a little bit change in this equation, okay, to some parameter that we can be much more easier to measure, okay, to look at how the energy change of the system. So let's say because of the time, let's take a 10 minutes break here. Then we'll continue to talk about this equation, okay, the thermodynamics of the aerosol. Okay, so let's take a 10 minutes break here, and then we'll continue at 12:45. Okay. Zoom the class. So that's a question from the student is just wondering the number of mole of all species, the second line. So I assume you're talking about this line, right? And then is it the K instead of the I, right? So this is we're looking at the species I, right? And then I is from 1 to K. Okay, depends on the number of species you have. And then you hold all other species, right, are constant. So I think that would be, no, the line on the top. Oh, you mean this one? Oh, so we assume there's a K number of K species. Does it make sense? So we have
唔係，因為我見到你寫number of moles of all species，第 open system 下面嗰個。
呢個啊嘛係咪？即係呢個 K 啊嘛。
上一行。
第一行呢個。
上一行。
呢個。
上面 number of moles of all species 係 K。
哦 ，OK。I see your point. Number of mole of species. OK, good. 即係呢個啊嘛係咪？你講呢個應該係 K 啊嘛。係。OK，OK， 我明你意思。其實我想講即係 species I 咁解。不過如果你呢個 A all 係你 confuse 係可以用 K 嘅問題，但我想講係 K species 咁解。但我明你意思係啊。答唔答到啲問題啊
？OK， 唔該。
Good。即係我So in general, I just want to say you have an I and then have total number of species K. So, but you're right. So you can put this as all species. Say if the total is K, then you can put a K there. Yeah, good. So just to confuse, that means that you have a number of K species. Okay, so that was NK here. Okay, very good. Okay. So any other question? Okay. So let's continue. So again, if you remember, right, so you want to use this equation, right? So one thing is that you want to look at how the entropy, right, entropy of your system change, or also the volume. So again, so just like I mentioned during the break, so this is not easy to measure, right? So you can argue, right? So this parameter, for example, so it's how to measure the entropy, right? So it's very difficult. So therefore, in terms of atmospheric science, okay. So for atmospheric science, so of course we prefer to measure. So using the temperature, and the pressure, right? So these are some parameters that we can be more easier, right, to measure. Okay. So therefore, in this case, so we introduce a new terms, okay, or new variable. So let's introduce a new variable. So we call this called the Gibbs field energy. Okay. Gibbs free energy. Kind of you can argue, right, the available energy, right, the energy that available. So therefore, I define G equal to so if you remember, so for the Gibbs free energy, it's kind of to look at, okay, the internal energy plus the pressure times the volume minus the temperature times the entropy, right? Entropy here. Okay, so kind of you are saying, if you remember by definition, right? This is we call the H, right? The enthalpy, right? The enthalpy term. And then you minus, we call the TS, right? In this case. So basically, we are consider, right, some available energy, okay? And then you take the differentiation, dg, so in this case, you take the differential, so you with U plus, so you hold the P, the pressure constant, and dV plus, you hold the volume constant by times you change the pressure, right? So therefore you have these two terms. And then you minus, right? PdS, and then also you minus SdT, right? So you hold the temperature, you take the differentiation, right, for your S, and then minus you hold S, the entropy constant, right, and the temperature. And then if you look at this term, okay, and then you can combine. So if you see here, right, so this is a change of the internal energy, right? So you have this expression, right, for an open system. So you say for some variable composition. So what you can do is that you can substitute this into here, right? And then if you take this substitution to here, so what you get, so what I'm doing is, so you have this expression, right? So, and then you can put this into this equation. So you will get this term, right? So now you can see, so when you talk about the change in your Gibbs free energy of the system will be equal to minus S times the dt plus the volume times the dP, change in the pressure, right? This is volume, this is pressure, plus some of the changes of chemical potential, right? This is your terms, okay? And also you can see, we can further simplify, or maybe before we move on. So now you can see, if you look at this equation, right? So you are looking at some parameter that we can be measured, right? If you look at the change in your Gibbs free energy of the system, okay, that will be like the change in the temperature and also a change in the pressure, right? So this is some kind of the parameter that can be more easier to measure, and also the change in your composition here, okay? And also, if you remember, so we are interested to look at a system. If you consider a system, say we again, so we're interested at constant temperature and constant pressure. So what will happen is, so in this case, that means your dt will be equal to 0, and also dp will also be equal to 0. So therefore, your equation, right, here will become more simplified, right, to the dg, right, changing your Gibbs free energy of the system will be just equal to this one, right? So because of these two terms, you will become 0, right? So you only look at your change in your Gibbs free energy of the system. So basically, you're looking at how the chemical composition change, right, due to the change in your composition, right? Chemical potential, right? So this is the change in your composition of your system. Okay. And then if I just make another assumption, So let's say if we make a further assumption, say your dn equal to 0. So that means your composition is also the same, or your composition does not change. That means your composition is constant for your system. So then if your composition is the constant, right? So it does not change. So that means dni, okay, or for all the species will also equal to 0. So this will be equal to 0. So what that means is your dg will be equal to 0, right? So this is how you can achieve a equilibrium state, right? If you remember, so dg equal to 0, changing your Gibbs energy equal to 0 means we are having we call the equilibrium, right? Okay, so if you don't worry about too much about these, we just quickly give you a quick overview about the thermodynamics. But one more thing is just to remind you that so most of the time, so when we talk about some equilibrium or some reaction, right? So of course we know we always talk about the Gibbs energy, okay? And also you can see based on what we're showing here, okay? So if you have eventually, so we show you say if your Gibbs energy change is equal to 0, right? At constant temperature and pressure, and also the composition is constant, then we are talking about the equilibrium state, right? So when you're changing your Gibbs energy will be equal to 0. Okay. So now you have some idea about the equilibrium. I also think that I also assume so you have some idea about the second law of thermodynamics. So basically, the second law of thermodynamics tells us the entropy, right? So of a system will increase. Okay. So when we talk about a irreversible process, okay, and then we always talk about the second law of thermodynamics. So I just highlight here is so your ds, right? So entropy has to be always larger or equal to 0, right? So your change in your entropy has to be larger or equal to 0. Okay, so because the idea is your system will always try to increase its entropy, right? So you always want to increase your entropy, okay, and then reach a maximum value at the equilibrium state. And also, most of the time, so we want to say that when you say your Gibbs energy, right, of the system, right? So the system will tend to decrease the Gibbs energy, right? So because this is the available energy, so we try to decrease or minimize, right, the Gibbs energy. Okay. So this is some just a highlight for your first law of thermodynamics. Okay. So now we want to look at some simple equation of single reaction, and then using the single reaction to talk about some Gibbs energy. Okay. So let's say if you consider a system, okay, to try to give you some idea about this concept, consider a reaction. A single reaction, so very simplified equation, a reaction, say A, and then you can have a reversible, okay, reaction AB should be, okay. And then, so let's say we consider at constant temperature and pressure. Okay. So now we just look at this and then see how you can apply the concept we have here. For example, when you're changing your Gibbs energy equal to 0, we kind of reach an equilibrium, right? So we just apply this. So let's say you have considered this a single reaction here. So we can first write a Gibbs energy, right? Gibbs energy. of your system, right? So it's not difficult to write down the Gibbs free energy of the system. Because you remember, right? So now we consider a situation, say, at constant temperature and pressure, okay? So when you look at the Gibbs free energy in your system, when you have constant temperature and pressure, right? So Gibbs free energy is just your chemical potential, right, of your species. So therefore, in this case, so your Gibbs free energy, right, at the constant temperature and pressure, right? So it's just your chemical potential, right, of the species. So that would be the Gibbs free energy of your system, right? Na is the number of mole of your species A. This is mu A is the chemical potential, right, of your species A plus. We only have 2, right? So this is the number of mole of your B times the chemical potential, right, of your species. Okay. So let's say we assume a system is closed. Then the system is closed. So if the system is closed in this case, so we can argue, right, the N total, the number of mole of your species, right, NT, the total number of moles of your species, so would be equal to Na plus Nb, so would be constant, right? The number of mole would be constant. So then I can just rewrite this equation. So I can just rewrite this equation. This is still the Gibbs free energy of the system, right? Now this is number of mole of A. I can replace this using the total number of mole of your system times XA. XA now is the mole fraction of the species A. So that means I can just replace this. Right, so I can just pick this NT, right? And then just if you time this will give you back the number of mole of A. And then the number of mole of B, I can just times 1 minus XA, right? So this 1 minus XA, right, will give you the mole fraction of your B, right? And then the mole fraction of B times the N total will give you back the number of mole of your B here. So this is just the mole fraction of B. So I just pick them 1 minus XA here. Okay. So then if I have this equation, right, for my cases, so if I have some idea about the chemical potential of my A and B, okay, so I can try to plot a graph like this. Okay, so this is, say, this is the system. Gibbs free energy. Right, I can calculate this, right? And then, so let's say the x-axis here is the mole fraction of my A, okay? This is my mole fraction of my A. So if I somehow, so that means 0 means that I don't have any, that means this is the pure, right? You only have the B. And then this is just that you have the, only you have the A here, right? So this in this case. So that means that we're still looking at this equation. And then this is a closed system. So now if you're plotting this, so you kind of the system, okay, the Gibbs free energy of the system. So you will see a curve like this here. So from the mole fraction of the A, okay, from 0 to 1. Okay, so this is pure A, this is pure B. And then if you look at this graph, so basically you can see you can kind of find a minimum point here. Okay, you have minimum point here. And then I can kind of derive into two regions, A and B. Okay, they can kind of agent A and B. So you can imagine, so let's start with our discussion, say in A here. So remember, right, so we know that for a system, right, so the dg has to be, tends to decrease, right? So that means that you can see, say in A region here, right? So we know that for the system, okay, your G, right, tends to be negative, right? So because the Gibbs free energy of your system, right, will tend to decrease, right? So because this is some available energy, right? So you try to minimize, right, your Gibbs free energy of your system. So therefore, what will happen in this case? So your Gibbs free energy tends to decrease, right? So for example, if a point in this region A, because in your system, right, the Gibbs free energy of your system will tend to decrease. Okay. So therefore, the system will shift to here, right? So we move to the right. So that means that in this case, the Gibbs free energy tends to decrease. So what will happen is your mole fraction of A will tend to increase, right? In this region A here. Okay. So that means in this case, some of your B will become A, will convert to become A here. And then if you imagine about the B, okay, or before we talk about B, so if you look at this, we have another point here. This is point C here, okay. So what will happen if your point moves, decrease, or Gibbs free energy of the system tends to decrease, and then you reach this point C, okay. Point C is a kind of the minimum, right? Minimum at point C. So you have the minimum, right? Gibbs free energy of your system, okay. And also you can see that the change, right, in your Gibbs free energy in this point, right, your dg will be equal to 0, right? In this case, dg will be negative, less than 0. So therefore, in this case, we kind of reach the minimum, right, Gibbs free energy of the system. And then you can argue, right? So your dg will be equal to 0. And also we can reach a kind of the equilibrium state. Or you can have this equilibrium state. Or you can have this, we call the equilibrium composition, right? So this is how you can look at, we call the equilibrium, right? So this is this one here, point C. But of course, you can argue, right? So if the system, right, is being forced to move away from this point C, so eventually, right? So for example, you try to increase the Gibbs free energy, right? But remember, so this is not allowed, right? So you will decrease, and then will give you, and then your system will force you back to this minimum point here, right? So then eventually you just stay there. Okay. So therefore, one more point is, so if your system is being forced to move away from the point C, that means your equilibrium point here, right? So it will return to, eventually it will return to the equilibrium state. Okay. Okay, so this is the kind of the ideas. Okay, found the Gibbs free energy. Okay, using a simple system, say we just consider a single reaction. Okay, to give you the demonstrate by using some concept. But the idea is, remember, you always the system always tends to decrease the Gibbs free energy of the Gibbs free energy of the system. Okay, That means for the system, the Gibbs energy tends to decrease. Okay. So this is the point. So that's why eventually, so you will reach just an equilibrium state in these cases of our equation. So this is just a consider a reversible reaction. Okay, A and B. Okay. So we can also try to look at some chemical reaction. So this is remember. So this is just a very simplified system or example to demonstrate. So about the equilibrium. Okay, equilibrium state of a system. Okay, and then we look at how we call the change in the Gibbs free energy of the system. Here we consider another cases. So now we consider a chemical reaction. Okay, so let's say we consider a chemical reaction. So how we can deal with this with the chemical potential. Okay. So let's say we have an equation. Okay, so let's say we also have a reaction, say A react with B, and then give you C and D, so it's a reversible reaction. And then you have this lowercase a, b, c, d. We call this a stoichiometric number, right? So you know this, we call this called the stoichio. So we follow the notation we use in the textbook. We have the positive sign for the reactant. And then we have the negative sign. That means this is a coefficient, okay, stoichiometric coefficient number. We have the negative sign for the product. Okay. So we also consider a more like a general chemical reaction. Okay, in this case. So now we can also analyze this reaction using like the Gibbs energy of our system. So again, so for the Gibbs energy of the system, so we have 4 species here, okay, and then you can write down the Gibbs energy of the system, right? So the Gibbs energy of your system will be just the number of mole of your species A times the chemical potential, right? Of your species A. This is the number of mole of your B times the chemical potential of your species B, number of mole of your C times the chemical potential of C, and then this is the number of mole of B, and then times the chemical potential, right? So this is what we did. So let me see. So let me change this to capital D just for the notation. Okay. So now because we consider reaction, right? So let's say again, so we want to have a constant temperature and pressure, right? So that's why you can have this equation. And then so let's say when certain amount of A is being reacted, maybe let me put down here. DNA. B means the change in the number of mole of A. So that means let's say this is called the number of mole of A reacted at a constant temperature and pressure. So this is the change in the number of mole of your A, right? Because we assume some A is reacted, okay? So because you are looking at the constant, right, temperature and pressure, okay? So if you remember, the change in the Gibbs energy will be also using this equation, right? We just show you here. Right, changing the dip energy of your system, right, will be equal to summation, right, of all the changes, right, in your composition and their corresponding chemical potential here. So then we can just using this equation, right, and then we can write up our equation. So therefore, changing your dip energy. So if you just rewrite this, so you just the chemical potential of your A times the change in your number of mole of your A, right? This is changing your Na, right? So this is changing your concentration, right, of your species I. That means the number of mole of your species here. So I just expand this equation, right? We only have 4 species and also their chemical potential, right? Okay, so now I want to express this equation, okay, in terms of like the number of mole of change in your DNA, okay, and the stoichiometric number here, okay. So I can rewrite this equation, okay, using this information. For example, so the dG will be equal to chemical potential of A, and then the amount of A changes, right? Or the number of mole of the A reactor, right? Plus, so now this is the chemical potential of your B, okay? And then this is the number of mole of your B reactor, right? So the number of mole of B reactor can be the number of mole of A reactor, right? And then by looking at the stoichiometric coefficient, right, or the stoichiometric number, right? So that will be equal to B divided by A times the chemical potential, right? Because I just write down here, B is the number of mole of your B reactor, right? This term will be equal to, right, the number of mole of your A reactor times this ratio, right, B divided by A, right? So this will give you the number of mole of your B reactor, right? So therefore, I can replace this term to here, right? So I can express the equation just using the stoichiometric number ratio here. Okay, I still have this chemical potential, and then this is the change in the number of mole of A. That means the mole of your A reactor. Okay, so this is just a play around with this one. So then I can also do the same thing, right? For the number of mole of C formed will be just a C over A. And also the D, right? So therefore, I can just express all these terms here, okay, with the change in the number of mole of A times their corresponding stoichiometric numbers, the ratio here. So just you don't need to write it down, so I just rewrite this more, because you have all this DNA, right, the number of mole of your A reactor. So I just take this out. So I just take this out here, okay. So now, if I'm interested to look at this reaction, right, and then we want to look at the equilibrium state. So we just show you for a system, right? So to reach the equilibrium, so the change in your internal energy, right, will be equal to 0, right? If I look at the equilibrium state, the change in my internal energy, the Gibbs energy of my system will be equal to 0. So that means that in this case, this term will be equal to 0, okay? And then you can rewrite this here. Will be equal to 0 because this DNA will take this to the other side, will become 0 here. Okay. So then you can see from this equation, so what you can get is at equilibrium. So you can just rewrite this, right? Looking at this term, it's just a summation of all your species. So this will be the general equation, right? So you can written down, and then now you can define. So this is we call the stoichiometric number, right? So but we can also express this, right, as what we call the stoichiometric coefficient. So again, the positive is for the reactants, and then the negative is for the product. Okay, K is the number of the species you have, right? Say, let's say AI here. So basically, this is the equation, right? Based on what we discussed about the Gibbs energy of the system. So this equation, right, will give you the condition. So maybe present the other way. Will give you the kind of the condition, right, of the equilibrium. Of a single reaction. Of a single reaction. Of course, you can expand this equation, right? So because we are now only talking about a single reaction here, so of course you can expand this to say to multiple reactions. So in that case, if you for multiple reaction, you just sum up and for multiple reaction here. But the thing is now you can have some more ideas about, so if you consider reaction, and then if you consider there's an equilibrium, okay. So how you can find, and then how you link to some chemical potential here, okay. But I'm sure, so now you still have some confusion, I'm sure, because now we use the term, I think you have some idea about this as stoichiometric coefficient, but you still here, right? So when you talk about the equilibrium, right? So we're talking about some chemical potential, right? So chemical potential. So usually this is not the parameter you use, right, in your calculation or in some of your classes. We are looking at the chemical potential, right? With that corresponding, like the stoichiometric coefficient of the species. And then if you do all the sum, then it should be equal to 0, right? So if you consider the equilibrium state for a single reaction or multiple reaction. Okay, so now we want to think about these chemical potentials. So what are these chemical potentials here? And then if you think about the later, when we do the sum substitution, then you will find that this chemical potential eventually come up with some equation that you are more familiarized. Okay. So now we want to look at some idea about these terms. So these are chemical potentials. Okay. So for chemical potential for species, of course, we can also have to consider different states. So for the atmospheric signs or aerosol, so we will consider like in the gas phase, and also sometimes it will be in the solution phase. That means your aerosol phase here. Okay, so now when we look at this chemical potential, so let's look at the chemical potential. For an ideal gas, mixture, okay. So if you look at a chemical potential for a species in the ideal gas mixture, so now we are looking at a chemical potential, okay, expression for a species, okay, in the ideal gas mixture. So you come across with this, the chemical potential of the species I. So I think you've seen this before. So the chemical potential of your species I, okay, in the ideal gas mixture, so will be equal to some standard, right? Standard state. That means your standard chemical potential, right, at some reference state. So let's say this is your standard. This is your standard chemical potential, right, of your species I. And then you're looking at the RT time. This is the pressure. The pressure here is the total pressure of the gas mixture. Okay. So this is P. P means the total pressure. And then the YI. YI is the mole fraction. The mole fraction of your species I, right, in the gas mixture. Okay. The YI here is the mole fraction of your species I in the gas mixture. And then you can see, because you can assume this is an ideal gas mixture, so these two terms can combine. And then you will find that if you times this YI times P, right? So that will give you, we call the partial pressure, right? So if you remember from your physical chemistry, partial pressure of your species I say PI will be equal to the mole fraction, right, of your species times the total pressure, right, of your mixture. Okay. So therefore, most of the time, people will combine this term, and then you'll find that the chemical potential of a species, okay, in the ideal gas mixture will be some standard chemical potential. I put a naught here, plus RT, right, natural naught, and then you have this PI here. Remember now the PI here is the partial pressure of your species here. So this is how you calculate the chemical potential, okay, of a species. We call in this ideal gas mixture. Okay. So this is ideal gas mixture. And also in the atmosphere. So we always also talk about the solution. So you have the water droplet, you have the aqueous droplet. So therefore, you can also talk about the ideal solution. So now we are talking about the ideal solution first, okay? So this can apply. So when we talk about some dilute solution, so then you can apply, you can assume this is we call this ideal solution. Basically, one idea is that the ideal solution is the chemical potential, okay, of all the components. It's more like a linear function, okay, linear function of the mole fraction, okay. So you can have the same, very similar equation. So you will also have we call the standard state, okay, or standard chemical potential. And of course, there are different states, so I put the star here, so I put the knot here. And then, of course, plus the RT, so because we were affected by the concentration terms. Okay. In this case, so this Xi usually is we call the mole fraction. So we use the mole fraction. Okay. The mole fraction of your species I, okay, in your solution, okay, it's the mole fraction here. So this is called the chemical potential. Okay. So now you have some idea and the expression for the chemical potential of your species, right? In the ideal gas solution and also the ideal solution. Okay. So let's say if you consider a cases, right? So we always consider a case. So you have a solution phase, and then you have a gas phase, and then you can assume there's an equilibrium, right? So kind of you can assume you can have an equilibrium, right, between two phases. Okay. And then you can assume there's an equilibrium, right? So let's say we consider this a scenario, and then you assume, okay, so let's say an ideal solution of I is in the equilibrium with also a ideal gas mixture. Okay. So basically, we just consider this. So we just present another way. So let me use a capital I in this case. So, but we just assume you reach an equilibrium. All right, so you can have this equilibrium here. So if you remember, so when we talk about the equilibrium, okay, so what that means is that the chemical potential, right? The chemical potential of your species in the ideal gas, in the gas phase, and also will be equal to the chemical potential, right, of your species in the liquid phase, right? So therefore, in this case, the chemical potential will be the same, right? So at equilibrium. So at the equilibrium, so basically the chemical potential of the species in the gas phase will be equal to the chemical potential, right, of the species in the liquid phase. So therefore, that means that these two terms will be equal, right? These two terms will be equal. So by writing this, so you have so you just have this term will be equal to this term, right? So these two terms are equal. Okay. So then if I rearrange this equation, so let me rearrange this equation. So you'll find that the partial pressure of the I will be equal to its potential So you can find that the relationship between the partial pressure, right, of your species I, okay, and the mole fraction, right, of the species I in the ideal solution. So you can have this correlation, and then this is exponential term, right, times the difference between two standard states standard chemical potential divided by the RT here. Okay. So now you may want to find about, so what about these terms here? So one thing you can think about this situation. So let's say if your xi equal to 1. So that means that you have a pure solution, right? So you only have that means that all the solution is you only have the xi here, the species I here. Okay. And then if you remember, so if your solution phase or xi equal to 1, right? So the partial pressure here, we can call this called the saturated, right? In this case, this is called the saturated vapor pressure, right? So because this will be equal to the vapor pressure, right, of your pure component, right? Pure component I, right? So if you remember, okay. So therefore, if you set this xi equal to 1, set this one xi equal to 1, so this one will become pi naught, right? So this will be your saturated vapor pressure, right? And then you will find that, so this term will become just the pi naught, okay, because this will become 0, okay, and then you will find that the pi naught so therefore, if you set this one, so if you do the calculation, so this term would become the pi naught. Because you can set this one, right? So would be equal to this term if you do the substitution. Because when you set this pi1, pi equal to 1, this term becomes 0. So this will become pi naught, okay, by definition. And you rearrange this equation. So this will become pi naught. So what that means is this term, the meaning for this term is potential, the difference between two standard chemical potential and then divided by RT. So this term, so actually, is your saturated vapor pressure, okay, or the vapor pressure of your pure component A here, okay. So this term, the meaning is just your saturated vapor pressure of your pure component A. Okay, so that's another question. So why does the partial pressure of species I become its mole fraction? Partial pressure. Okay, so the partial pressure of your species will be the mole fraction, right? Of your species I times the total pressure. Does it make sense? Yeah. So this is you times the partial pressure is the mole fraction times the total pressure. So give you the partial pressure. So therefore, you can see here is the partial pressure. So basically, this equation tells you, of course, this equation, the idea is to tell you between the relationship between, say, if you know the concentration, okay, of your species in the solution, then at equilibrium, so you can calculate, right, or predict the partial pressure, right, partial vapor pressure in the gas phase, right? And then how you can relate this, so you can relate it also related to the concentration of your solution. This is the partial pressure of your species in the gas phase, so you can link to the saturated vapor pressure. But now here you use this is the mole fraction of your solution phase. Okay. So this is a different. I think this is a different from what you mentioned in your question. But the idea is this equation more likely to tell you the vapor pressure, okay, of a species I. So over the solution. Over the solution. So if you know the concentration of the solution, and at equilibrium, you can predict the vapor pressure of the species I here. Okay. So you may have seen this equation before. Actually, this equation, so it's more like the Raoult's law. The Raoult's law basically tells you if you know, okay, the concentration of your species in your solution phase, and then you can just estimate or predict the vapor pressure of the species in the gas phase, and then using the saturated vapor pressure. Okay. So because of the time, so let's take a second break here, okay, and let's take another 10 minutes break here, and then we'll continue. And then talk about so how you're going to predict the gas phase, the vapor pressure, okay, and then using the Raoult's law or that we call the Henry's law, okay. So we're going to talk about this. Let's come back at 150, okay. Any question from the class? So any question? So again, so feel free to stop me anytime or just type your question in the chat room. So I'll try to answer this. Okay. So now we'll go back to this equation. So you can see this equation, right? So I think we have seen this before. We call the Raoult's law. So basically, it tells you the relationship, right, between the vapor pressure of the species over the solution, right? If you know the concentration. So you can see we just present in another way. So start with the chemical equilibrium, GSP energy, chemical potential, and then we come up with this equation. Right? So I think we just show you this equation before. But what we show you here is just to say start from thermodynamics, the GSP energy, delta G equal to 0. So we show you how you come up with this equation here. And now you have some more ideas. So when you talk about the saturated vapor pressure, right? So what's in terms of like some chemical potential, right, or standard chemical potential of those species, right, between two phases here. So then you have some more ideas. But more the application is so how are you going to use this equation or under what situation, right? So you can use this equation for the Raoult's law. So Raoult's law means that if you know the concentration, right, of your species in the solution phase, you times the saturation vapor pressure, then you can predict the gas phase concentration, right? So this is the Raoult's law. And I also think that you have come across another equation called the Henry's law. So Henry's law also predict, right, this equation. So if you remember, right, so this is the Henry's law. So Henry's law tells you, say, this is your Henry's law constant for your species A. If you know the partial vapor pressure, right? I mean, if you remember, right, so for Henry's law, if you know the partial vapor pressure, okay, of your species, and then you can predict your, say, your aqueous phase. So this is more like the aqueous phase, right, of your species, right? The concentration using the Henry's law constant here. So you can see it's a very similar, right, to what we have here for the Raoult's law, for the Henry's law. So, but there's a difference, okay? So when we are going to use these two equations, okay? So first, let me draw your figures, okay? So to tell you, so under what situation or condition, so you're going to use the Raoult's law. Under what condition you're going to use the Henry's law, okay? So let's say we consider a binary solution. A binary solution. So just consider A and B. So we only have two species, A and B here. Okay. So then you will have a graph like this. Okay. So the x-axis here is the mole fraction of your A. XA is the mole fraction of your A. So that means if a mole fraction of A is 0, so means that this is called a pure B, right? So we have B here. And then if your mole fraction is 1, so that means this is only your pure A, right, in your solution. Okay. And then for pure B, right? And so for say your mole fraction equal to 0, pure B, you can argue, right? So you have a PB log. So your saturated vapor pressure, right, of your P, of your B, right? So I think this makes sense, right? Because when your mole fraction of A is 0, so that means your pure B, right? So that means at this point, the vapor pressure would be just the saturation, right? Or saturated vapor pressure of your pure B, right? So at this point here. And then if this is the mole fraction is equal to 1, so that means your pure A. So that means that you will have a mole, this is your saturated, right, vapor pressure of your A, right? So maybe let me okay, so this is your saturated vapor pressure, right? For pure A. So this is your saturated vapor. Oh, pure B, right? So these 2 points. Okay. So then if you have this mixture, right? So if you're kind of a linear, right? So you can argue, right? The pressure, right? So you can argue if you have this pure B, if it's just a linear relationship, so you will have kind of like this linear relationship. So you have this. Okay. So these lines. So this line will give you the partial pressure of your B. And then this line will give you the partial pressure of your A. I think sometimes ago you know, right? So if you add this up, so this is the total pressure, right? So this is the partial pressure of A plus the partial pressure of B, right? So if this is the ideal solution, you just have a relationship like this, okay? So now, so how are we going to use these two equations? So you're not going to apply for the whole range, okay? So there's some limitation, okay? So here, for Henry's law, so let's start with this Henry's law. So I think we show you this Henry's law in some of my classes. So this will only valid for a dilute solution of A. Dilute solution of A. Okay, that means you have a low concentration of A. So if you remember, right, so when we use the Henry's law, so when we're going to Henry's law, we apply to the cloud droplet, right? So when you have a cloud droplet, so most of the time you have water, you only have your concentration of A is very diluted, right? So low concentration, you can use the Henry's law. So therefore, in this case, so if you want to predict the vapor pressure in this graph, okay, so you can use the Henry's law only when the concentration of A or your solute concentration is low. So therefore, you can apply the Henry's law in this region. So you can predict, right? So this is because the mole fraction of A is low, right? So therefore, in this case, so you can predict using the Henry's law, right? So in this case, you can predict that using the Henry's law. Or depends on how you write this, but the idea is that you can use the Henry's law to predict the vapor pressure, okay, using the Henry's law constant in the dilute situation. Okay. So this will also apply for your B, if you want to predict your B, the partial vapor pressure of your B, so you can also using the Henry's law here. Okay, because when your mole fraction, right, is close to 1. Okay, so that means that you have most of them is A, only a small amount of B, right? So therefore, B is also fulfill this concentration, this situation, right? So you have a low concentration of B. So therefore, you can also predict using the Henry's law constant. Okay, in the dilute situation for A and B. For the Raoult's law, in that case, actually the Raoult's law actually is more for the, we call the solvent. The Raoult's law. So if I want to say for the Raoult's law, so it's a more valid for the solvent. Okay. So what that means in this case, when you are solvent means that you have a high concentration, right? In this case. So therefore, if you want to predict the high concentration of the solvent in this case, so here, let's say take the extreme here. So this is as close to the pure A, right? So that means that most of your species are A. A is more like the solvent, right? Because the solvent is the high concentration, right? Compared to your solute, right? So your solvent, for example, your water, right? So water is a solvent, right? So you can consider A is your water in this case. So therefore, in this case, so if you want to predict the A, okay, in this region, then you need to use the Raoult's law. So you will predict your species A using the Raoult's law here, because you can see, right, in this situation, right, so A is a high concentration, so you cannot use the Henry's law, right? So therefore, you use the Raoult's law here, because A is more like the solvent. So therefore, in this case here, you can also argue in this point, so you're going to use the Raoult's law, right, for the partial pressure of your B, right, using the Raoult's law here. So therefore, the idea, the concept is when you want to use the Henry's law, you are looking at some dilute. So that means your concentration of your species should be low. Okay, that means that you're looking at the dilute solution of your species. That means your concentration of your species has to be low. Okay, so one scenario is like we mentioned, right, in the cloud droplet. Okay, so if your concentrations become high, then you should not use the Henry's law. So now you should use this called the Raoult's law. Okay, so for high concentration, if your species concentration is high, okay, so that means in these 2 points, if you want to predict the partial vapor pressure of your A, then you should not use the Raoult's law. Then you should not use the Henry's law. You should use the Raoult's law, because your concentration of your A is high. Then this is use the Raoult's law here. Does it make sense? So this is basically tells you under what condition or situation you should use these 2 equations. So again, so the dilute solution, you use the Henry's law. More concentrated solution, you use the Raoult's law. So this is the rules, okay, for your information. Okay, so now every time when we talk about this graph, right? So we always talk about ideal solution, right? Ideal solution. So because you have the ideal solution, you can kind of you have this kind of a linear relationship, right? So you have this linear relationship. So you have this straight line here, right? And then if you look at your total vapor pressure, you have also, you just add them up, right? For your total pressure, right? So this is, I think, but you know, we are not always in this we call the ideal solution, right? So we can always have this we call the non-ideal solution. So usually this is good for ideal solution when you say we have the dilute cases or dilute solution. So you can assume this, we have some ideal solution, right? So we can argue like this. But in the atmosphere, for example, we talk about aerosol. So aerosol, you can be a droplet, right? Or aqueous droplet. So we are not in this, we call the ideal solution. So because the idea is, so let's nip it down, this is called the non-ideal solution. Non-ideal solution. So because the idea is the aerosol, so you can imagine, so for aerosol, it can be an aqueous droplet, right? So aerosol, you can also argue it's an aqueous droplet. And then you dissolve the species. So the aerosol, most of the time, okay, of course, it depends on your composition or your environmental condition. So aerosol are usually concentrated solution. So we are looking at some concentrated solution. Okay. So unless you talk about the cloud droplet, but if you talk about the aerosol, we are talking about some concentrated solution. So therefore, it is always deviated from the ideal solution. Okay. Not an ideal solution. So therefore, to correct this, right? So we will introduce a terms, right? So let's say if you want to look at the deviation, say from the ideality. So you can be described by a terms called activity coefficient. Activity coefficient. We'll call the gamma I here of your species. So because you use this term to correct the deviation from the ideal solution, right? So this is called gamma. So therefore, the chemical potential, the equation we are looking at now, especially for the solution. Okay. So now you need to consider this deviation from the ideality. So you will have this term. Right, so you need to times this activity coefficient, right, into your solution, in your solution phase, okay, in your aerosol, okay. So to do the correction, so this is called the activity coefficient. This is the concentration terms, right, like the mole fraction or molarity. So, but the one thing is more precise to describe is that we use the term called activity. Okay, we use the term called activity because you use the activity means because you have already correct this non-ideal situation, right? So in case it's significant. So therefore, usually we talk about it's called the activity. So the activity basically means is the mole fraction of your species I, that means your xi, times the activity coefficient, okay, of your species I. That means gamma I. So therefore, usually when we talk about the activity, when I talk about the solution phase, so we always talk about is the activity, okay. So you always need to do this correction here. Okay. Just one more thing we want to highlight here is, of course, from time to time we use the mole fraction, but some of the time, so people will use the molarity and also the molality, right? So they're different, right? So the molality and molarity. So for the molality, here means you are talking about the number of mole, okay, of your species, right, per, say, the mass of your solvent. For example, a kilogram of your solvent. So that means that you're looking at mole and then divided by the mass of your solvent here, okay. But sometimes the molarity is different. So for the molarity, so you are looking at the volume, okay? That means that you're looking at the number of mole of your species. But now you are looking at the volume of your solvent. So that means that now you say it's a per liter of your solvent, okay? So you see the difference. So one is by the mass. For example, you're using a kg of your solvent. Sometimes it's the volume of your solvent. So sometimes we need to pay attention because if you use the volume, so somehow you need to pay attention to the temperature and pressure, right? Because the volume of your solvent sometimes will depends on the temperature and the pressure, but the mass it does not. So this is just for your information, okay? Okay. So now you have some more idea about so the chemical potential, and then using the gas phase, liquid phase, and also the solid phase here. Remember for the solid phase, so because the chemical potential for the solid phase, if you remember, just write down here, the pure solid. Because you're looking at the pure solid means your mole fraction equal to 1. So the chemical potential of your solid it's just some standard chemical potential, okay? It's just some standard chemical potential. You don't need to worry about the composition terms, right, or the concentration term, because so we are talking about some pure solid. So therefore, the chemical potential just some standard chemical potential at reference state here. Okay, so now we want to go back to some of our equations and then try to understand, say, from the chemical perspective or the Gibbs-free energy. So we want to look at another term. So for example, the equilibrium constant. And then how we can link this equilibrium constant K, right? I think we use this equation, the equilibrium constant, right, so many times. But how you can link these to the chemical potential, right? Or what we talk about the Gibbs-free energy or Gibbs-free energy equal to 0. So this is also relevant to the aerosol chemistry, because most of the time, some of the reaction or the gas particle positioning, we always talk about some equilibrium. Okay. So let's say we try to look at some aerosol equilibrium calculation. Okay. And then now we look at some maybe related to the solution phase. But for example, in general, so if now you have the idea, right, for the general reaction. So at equilibrium, right? So we know so we have this equation show you at constant temperature, constant pressure, right? At equilibrium, right? So this is just the chemical potential, right? This is 1 equal to 0, the summation of this stoichiometric coefficient of your species. This is the chemical potential of your species. So will be equal to 0 at equilibrium, at constant temperature and pressure. So now if you consider a solution reaction, okay, in this case, so you can have an expression for your chemical potential terms here, right? So you can have a chemical potential term, right? So let's say we bring it more in general. Okay, so not just the solution, maybe the gas phase also. But the idea is, remember now when you look at the concentration terms, so you need to look at is the activity. Okay, so more important is to look at the activity, right? So you're not looking at just the concentration here. So you need to correct the deviation from the ideal solution. So therefore, if in this case, we still use the liquid phase as an example, maybe. So therefore, we need to put down is the standard state or standard chemical potential plus RT, right? And then now you know this is now not just, we don't just use the mole fraction, right? We use the activity, right, of your species, right? So because we also want to consider the deviation from the ideal solution. So then what we can do now is we can just take this out, take this term out. So what you can do the summation term, take this out, and also have another summation term here, right? If I rearrange this equation, so you have this term taken out, but I take just the 1 over here. So you will have two terms. One is the summation of this term, right? This coefficient times the chemical potential, right? And then plus the RT natural log, right? Times this summation, you have this term. But I put the RT, okay, to this side. I put this term to this side, and then the RT, I just come back to the other side. So that's why it's minus 1 over RT times this term will be equal to just the summation, and then Stoichiometric coefficient times this natural log, and then this activity coefficient. I just play around with I just put this here, and then just move the 1 over RT to the other side. And then if I have the natural logs here, so I just pick the exponential terms at both sides. Okay, so I just take the exponential on both sides. So what do we get? So you can apply some rules. So if you still remember from the lateral logs, so that would be lateral log B over A. And then if you remember the exponential lateral log A plus lateral log B plus lateral log C, so that would be equal to the lateral log A so you get ABC. So if you apply this, come back to here. So this will give you so I overrun a little bit. So let me just finish this equation here quickly. So if you rearrange this equation, you will find that on your left-hand side, so this term, okay, so it will give you this expression, okay. And then if you look at this right-hand side here, so actually this will be just your equilibrium constant, okay, of your species I, of your reaction, okay. And then this is just your equilibrium constant. Okay, so I think because of the time, let me stop here for today. Okay, I will come back to this and then explain to you, starting from here, and then so it turns out you can calculate your equilibrium, okay, calculate this expression, okay, and calculate the equilibrium constant by looking at some of their chemical potential. Okay, so we're going to come back to this in the next lecture. Okay, but before we leave, do you have any questions from the class? So again, so we just come with you from a different perspective. I'm sure you know how to use the equilibrium constant with some of these terms here. So you know how to do this. We just show you another perspective, okay, from the chemical potential thermodynamics point of view. But we're going to talk about this equation in the next lecture, okay? So if there's no further question from the council, I will see you on next week. Okay, thank you. Bye-bye.